Hello everyone, my name is Ajay Merdi. In this presentation, I am going to discuss about combustion characteristics of a liquid-fueled ramjet combustor. Abstract. The spray and combustion characteristics of a liquid-fluid ramjet combustor were experimentally analyzed. RJ-1J fuel was injected transversely into a subsonic hot aviation stream from a round injection orifice. The penetration of the liquid jet under hot air row conditions was larger than the calculated by the empirical equation obtained under room temperature air row conditions. A V-shaped gutter was attached to the center of the combustor for ram holding. Two different arrangements of the gutter and the fuel injector were tested. In one, the fuel was injected perpendicularly to the gutter axis, and in the other, the fuel was injected parallel to the axis. In regard to perpendicular fuel injection, a region with a temperature higher than 1500 Kelvin was observed at the center of the combustor. This region was long and narrow in the direction of the fuel injection. The high temperature region reached the bottom wall due to involvement of the fuel in the wake region of the fuel injector and the liquid column. In regard to parallel injection, the high temperature region covered the major part of the cross section of the combustor except in the vicinity of the bottom wall. The measured pilot fuel injection from the gutter was found to be very effective method for improving combustion characteristics. In addition, it was found that the fuel dispersion in the direction of the injection of the high temperature fuel, which stimulates the regenerative cooling of a ramjet combustor, was lower than that of the low temperature fuel due to fuel evaporation. Introduction. Storable liquid fuels attractive for use in the volume limited ramjet engine due to its high density and high heating value. However, it requires evaporation and time to mix with air before ignition. Insufficient evaporation and mixing result in low combustion efficiency and instability. On the other hand, liquid fuel can mix with combustion air because of its large inertia. Therefore, the disadvantage of liquid fuel may be compensated for by improving its spray characteristics and devising a means of mixing fuel droplets and combustion air. As for the direction of fuel injection, transverse fuel injection into a high-speed airstream has been commonly used because it results in large penetration and through mixing between fuel droplets and air in comparison with parallel injection. Other researchers have studied the penetration and jet width of a traversing liquid jet in a supersonic airstream in regard to using these features in a supersonic combustion ramjet. The penetration and jet width of traversing liquid jet in the subsonic airstream have also been studied in regards to their use in the afterburners of gas turbine engines and liquid fuel ramjet combustors. Most data in the cited studies were obtained under room temperature airflow condition. However, the spray characteristics of a traversing fuel jet under the actual hot airflow conditions are very important for comparison with those obtained under cold flow conditions. A V-shaped gutter is generally used due to low pressure loss and the high performance of a flame holder. In this presentation, the conventional configuration of transverse fuel injection and a V-shaped gutter were employed. Here, the combustion characteristics depend on the combination of the direction of the fuel injection and that of gutter axis. However, previous research has not clarified the effects of this combination on combustion characteristics. Several researchers have examined the combustion characteristics of a liquid jet in a supersonic airflow as well as those of a gas fluid ramjet engine. However, there have been few studies on the combustion characteristics of a liquid fueled ramjet engine. The aim of the present series of studies is to clarify the relationship between the spray and the combustion characteristics of a liquid fluid ramjet combustor. In this study, penetration of a liquid fuel jet into a hot stream were measured and were compared with those under cold flow conditions. Firing tests of RamJet combustor were carried out for the following two examples. One in which the liquid fuel was injected parallel to the gutter axis, and the other in which the fuel was injected perpendicular to the axis. The combustion characteristics such as flame holding ability, temperature distributions, combustion efficiency, and total pressure loss were examined. Experimental apparatus and conditions. The experimental apparatus is shown in figure. The RamJet combustor, which is made up of stainless steel, has a rectangular cross section of 50 mm and a length of 563 mm. The fuel injector, which projects into the airstream, is attached to the bottom wall. The V-shaped gutter, the axis of which the perpendicular or parallel to the direction of liquid injection, is fixed at the center of the combustion. Static pressure tapes are mounted on the upper wall in the direction of the airflow. Ventilation, hot air which is generated by mixing the air with a combustion gas of gaseous oxygen hydrogen, passes through the combustor from left to right. A jet of liquid fuel is injected transversely into the hot stream. The exit of the gaseous hydrogen torch igniter for ignition is located on the bottom wall just below the gutter. After ignition, the supply of oxygen hydrogen is cut off. The distance between the exit of the fuel injector and the gutter in the direction of fuel injection is variable, and the distance between them in the direction of the airflow is variable. The horizontal distance between the gutter and the exit of the combustor was maintained at 400 mm during all of the present experiments to avoid effects of axial length of the combustor and combustion characteristics. For ease of observation, both of the side walls of the combustor can be replaced by crystal glass plates if necessary. Figure 2 shows the fuel injection in detail. 3 fuel injectors were used. They were made up of stainless steel with inner diameter of 0.5, 0.7 and 1.0 mm. Each fuel injector has a length to diameter ratio of 9. The entrance of a straight passage with a diameter of d was polished so that no turbulent flow. Figure 3 shows that the configuration of V-shaped gutter, which is made up of stainless steel. The cross section of gutter is triangular and its blockage ratio is 0.2. Gaseous hydrogen fuel is ejected parallel to the airstream from 15 holes that are 0.5 mm in diameter on the leeward surface of the gutter. It was expected that gaseous hydrogen would act as pilot fuel and would promote flame holding. Jet penetration in a hot airstream. Estimating the penetration of a fuel jet into an airstream is very important for RamJet combustor design. In previous presentation, the authors detected the empirical equation of jet penetration under cold flow condition as follows, where jet penetration was defined as the vertical distance from the bottom wall of the combustor to the outer edge of the fuel jet fume as measured by time average photographs. The jet penetration is a hot stream was measured in the present study. Figure 8 shows the variation of the jet penetration in a hot airstream by the fuel to air momentum flux ratio and the fuel injected diameter. The jet penetration increased with an increase in the momentum flux ratio. The jet penetration increased rapidly in the vicinity of the injector exit and then generally increased due to the increase of the drag of the airstream. The cross section of the jet is circular at the injector exit. It then becomes kidney shaped due to the dynamic pressure of the airstream. This shape transformation results in an increase in the drag. The liquid jet was disintegrated into liquid lumps due to the large scale waves on the jet surface. After the disturbance waves on the windward surface of the liquid jet grow to some extent along the jet's trajectory. The liquid lumps were disintegrated into finer droplets again due to aerodynamic force. The momentum of spray droplets in the direction of the liquid injection gradually decreased due to the gravity and the drag force, and in the direction of airflow. It increased due to the acceleration by airflow. Consequently, the penetration curve of the spray plum approached the airflow direction. Figure 8 shows the impact of fuel injector diameter on jet penetration. The larger the injector diameter is, the further the fuel jet penetrates. The effects of injector diameter can be attributed to differences in the drag of the jet with unit volume by airflow. As the injector diameter decreases, the drag of the jet stream. The liquid jet was disintegrated into liquid drums due to large scale waves on the jet surface. After the disturbance waves on the windward surface of the liquid jet grow to some extent the jet's trajectory. The liquid lumps were disintegrated into 500 droplets again due to aerodynamic force. The momentum of spray droplets in the direction of liquid injection gradually decreased due to gravity and drag force, and in the direction of airflow it increased due to the acceleration by airflow. Consequently, the penetration curve of the spray flume approached the airflow direction. Figure 8 shows that impact of fuel injector diameter on jet penetration. The larger the injector diameter is, the further the fuel jet penetrates. The effects of injector diameter can be attributed to difference in drag of the jet with unit volume by airflow. As the injector diameter decreases, the drag of the jet by the airstream. Maximum and minimum equivalence ratio. Table 2 summarizes the maximum and minimum equivalence ratios using Vitation's air where flame holding was confirmed and of parallel fuel injection under various experimental conditions with pilot hydrogen fuel injection. The pilot hydrogen fuel was always injected during measurements. The representative air velocity and temperature those measured at the center of the combustor inlet. The experimental uncertainties for equivalence ratio calculations were estimated to less than 4%. As will be discussed later, the combustion efficiency for perpendicular fuel injections is much lower than that of for parallel fuel injection. The equivalence ratio range where flame holding is possible for perpendicular fuel injection was not studied in detail. Figure 11 shows the temperature profile under high air velocity and low air temperature conditions for parallel fuel injection with pilot fuel injection. The temperature region that is higher than 1500 Kelvin is long on both sides in contrast with that of perpendicular fuel injection. Here the fuel vapor and droplets are pushed aside towards the side walls due to gutter. The temperature region is somewhat broader than that of perpendicular injection in spite of having a smaller equivalence ratio. In figure 10, the temperature region that is higher than 1500 Kelvin is about 30% of the combustor cross-sectional area, whereas in figure it is about 38% in case of perpendicular fuel injection. The amount of fuel that collides with the gutter is limited. However, in case of parallel fuel injection, most of the fuel collides with the gutter. Conclusion: automation and combustion tests of a RamJet combustor were carried out to analyze fuel jet penetration and the combustion characteristics of two types of fuel injection. Conclusion can be summarized as follows. Although note that because the experiments were conducted under limited experimental conditions, the following conclusions cannot always be directly applied to the condition in generator. The fuel jet penetration in the hot air flow with temperatures of 630 and 903 Kelvin and a velocity of around 60 meter per second was much larger than that of calculated from the imperial equation that was obtained under cold flow conditions in the previous presentation. Second one, the maximum and minimum equivalence of the example with an inlet area temperature of 600 Kelvin and an air velocity of 100 meter per second are higher than those of the example with air temperature of 900 Kelvin and air velocity of 660 meter per second, possibly due to fuel dispersion. That one, the equivalence ratio range under high temperature conditions with a temperature of 900 Kelvin and a velocity of 60 meter per second is wider than that under air temperature condition with a temperature of 600 Kelvin and a velocity of 60 meter per second due to promotion of fuel evaporation. Under conditions with an inlet air temperature of 600 Kelvin and air velocity of 100 meter per second, the temperature region that is higher than 1500 Kelvin in the cross section for the parallel fuel injection is broader than that of perpendicular fuel injection. The measured combustion efficiency in the case of parallel injection is higher than that of in case of perpendicular injection. Thanks for watching.